Okay, so let's begin as this recording as it is. So we're going to be looking at week 9, but it's more than just week 9, we're just going to be looking at the second part of week 8. Let's actually fix it. So we looked at hash tables already, we're going to be looking for functional stuff onwards. As you can see here, we talk about functional stuff here. And then we're going to be going into stable sorting and non-stable sorting, and then towards the end we'll go into is-stable sort. Now, typically we actually write this function, but this is one of those functions that I actually think the code for is to be the code that's actually provided is typically wrong, for a few places and stuff like that. So instead, what we're going to do is we're just going to have a look at it. It's pretty straightforward, and then we can just kind of go through what it does. This is a function that you don't really need to know too much about. And then we need a selection sort that builds a new version, which we'll go into 2. I don't think I've written one. I think I've written everything but selection sort in week 9. Let's see. Yeah, I've got a bunch of example sorts here. Oh, no, this is a selection sort, but this doesn't create a new array. So it would be pretty easy to create. So maybe we'll get right into this. We may not. We'll see. I prefer not to do coding questions like when I record things because I think they're not as useful as if I do them step by step and you can ask questions and so on. Otherwise, I'm just kind of writing the code and you're watching. It's not really useful, I think, at least. So anyway, so we're going to begin by looking at sorting because I think that's useful, and then we'll pop into the actual stuff. So there's really, I think it's 6 sorts. Yeah, it's 6. So there's 6 sorts that we typically cover in this course. There's bubble, there's insertion, merge, quick, selection, and shell. Shell sort's probably one of the odd one out in terms of that it's not really like any of the others, and typically it's probably the least important one. Bubble sort's probably the one that you're most used to. Basically, all you do, as we can see here, is we're just going to loop for each element, low to high, and then we're just going to basically swap all the elements down to that lowest element that we just have, and we're just going to swap them all the way down, right? So we end up with a system that looks like this. We have 1, 2, 3, 9. Actually, I should do that. 2, 1, 4, 3. Let's say, right? So what we're going to do is we can begin at this spot, and what we want is we want to swap down the smallest element. So we're basically going to do a full swap all the way from this position all the way to the end, right? As you can see here. And typically, if I was on this course, we actually show you by starting at high, but you could start low and just go all the way through the array and stuff like that. So this is a much more optimal bubble sort. It does the least number of work. It's still n squared, but it does quite a bit less work, especially for fairly large arrays. But effectively, it's the same idea, right? So what we're going to do is we're going to basically begin by saying, okay, our I here is this, right? And then we're going to set j to the last element. All right, and what we're going to do is we're basically going to move j all the way down, but we're not going to go past I, we're going to stop just before I, so we're going to stop here. And for each element, we're going to see if we want to swap it with the previous element. That's all this is doing, right? So instead of swapping forward, we're swapping backwards. It's just a slightly different way of doing things, but the benefit is that we can stop at I, whereas the other way would be that we'd always have to begin from the beginning and go all the way through, right? So we save a little bit of efficiency. I believe this is what the course goes through. So anyway, so we're going to begin, and so the first iteration, it's going to swap the 3 and the 4. And then it's going to go, okay, these two can also be swapped. So these are going to swap. Wait, no, it can't. I'm wrong. I was like, wait, that's not right. That's fine. It will swap the 4 and 3 because 3 is less than 4, but it won't have to swap the 3 and the 1 because 1 is less than 3 already, so it doesn't need to change that condition. And it's going to look at the 1 and 2 and swap these, right? So we're going to end up with 1, 2, 3, 4. Okay. And then, and so on, right? So really, if it's got multiple iterations, the worst case I think is when you have something like this. Yes. So what will happen is it will swap. This is our I, this is our J. It will swap the 1 and the 1 and 2 will have to be swapped because the 1 has to be before the 2. So it's going to become like this. Right? And then it's going to go, okay, this 3 and this 1 should also be swapped. So you get, like this. And you notice this 2 gets left behind. And then it's going to go, okay, the 1 and the 4 can be swapped. So we end up with this. So 1, 4, 3, 2. And then it performs the entire thing again, but now it can start from 1 instead of starting from 0. So our I becomes here and our J becomes here, right? So it can move the I up because it knows that this has to be the smallest value. So then it can swap these two, and we end up with 2, 3. Swap these two, we end up with 2, 4. So now we're ending up with 1, 2, 4, 3, and I will be here, and J will be here, and it's obviously pretty obvious that the last iteration will just be swapping these two, so that we end up with 1, 2, 3, 4 as required. Okay, great. The next one is quick sort. Quick sort's a bit of an unintuitive one. I will quickly go through. I'm not going to go through all the sorts. I'm just going to do quick sort and bubble sort, and a quick one on merge sort. Then I'll just talk briefly about these two. So I'm going to do it very quickly. So the basic idea of quick sort is that you make partitions. So what you're doing is you're making a partition where you want to split it such that everything past this value is greater than this, and everything less than this value is to the left, right? So you're creating a partition in this set. Right? As you can see here. So effectively, if we go back to one of our examples, I think we're just going to go back to 4, 3, 2, 1. Then we're going to add another number just to make it odd, because it makes the partitioning a bit easier to see. Also, we're going to partition on an even number, so we're always going to partition on the middle, just because it makes life a bit easier. Or rather what we call the middle elements. There's a few ways you can do it. There's median, which is you basically grab the middle element if it was sorted. So you kind of find all the values and you find the middle value if it had to already been sorted, right? So in this case, the median value is going to be 2, right, if it was sorted. So regardless of the ordering, the 2 is always going to be the median value of this set of numbers. The other way is you can do random. Random is actually pretty good. So this is, I believe, typically the best method, and this is typically actually turns out to be one of the best methods as well, but typically it's a little worse than median. And the third way is you always choose the same pivot point, right? So pivot constant, right? So maybe you always choose the maximum one, which is typically pretty bad, or you just always choose the middle one, right? So you always choose like index 2 out of 5, for example. Well, this would be 3 out of 5, but you get the point, right? Or rather, it would be the second index out of 4 indices, because 0, 1, 2, 3, 4, right? Now, it doesn't really matter. You want to choose your index point, and then you basically want to sort it so that everything to the left of it is less than, everything to the right of it is greater than. You don't actually care about the actual ordering of those, you just care about doing it so that the condition holds. And so what we end up with is typically we try to keep the ordering the same just because it's simpler. We just kind of like move all the variables across. And so we're going to end up with this, right? So our condition holds on both sides. And then what we're going to do is we're going to do the same thing on each of these two subarrays. So this goes down, and we're going to end up with this same thing here. Now in cases like this, what pivot do we choose? Doesn't really matter, but we're just going to say whenever we land in the middle of an even number, we're always going to go right. So our pivot point becomes 0, which means that we get 1 has to come on the right side of 0 because we have to have everything to the right be greater than, right? So we get 0, 1, and that's our first one, and then we get 2 again, that doesn't change, and then in this case we get 4 on the right, and then 3 has to become on the left because we want to be less than, right? And then what we're going to typically do is either we typically detect this case of 2, because the case of 2 is basically the base case. There are base cases where we end up with 1, but typically that doesn't happen because pivot points always cut it down by 1, right? So we always get rid of those evens. But for example, if you just have a single element and you try to sort it, you're going to end up with a base case of 1. So typically what we do to detect these base cases is this condition here where you say, hey, if our low is equal to our high, that basically means that you're pivoting on a single point, right? Or if it's greater, that means like the bounds are weird, but typically it's when it's the same, right? So in this case, we'd be like pivoting and we'd say, okay, sort 0, which is already sorted, so you don't have to worry, right? And so this is the quick sort end result, is this thing here, right? So you basically just split up the array into 2 every time. Merge sort is the exact same idea, but the difference is it halves the thing and then it merges each of the sides, so it splits into 2, merges each of the sides. I don't think I've got an example here, and then just combines it back together. So in this case, it's going to split this into 2. We can get 4, 3, 2, 1, 0. Sometimes the 2 is included as a separate array, sometimes it isn't. Typically it isn't. I'm just going to include the left side for this example. We get into with this, we're just going to keep repeating, right? And so then in this case, we're going to get 4, 3, and 2, right? And then we get 1, 0, right? And then 1, 0 is going to be split up, and then finally 4, 3 will be split up as well, right? And then once we've split them all up into a single element, when we combine them back together, we're going to make sure that they're ordered. So we're basically going to do like linked list, I think it was called insert in order, was the first lab. Right, and this is effectively what you're going to be doing for a linked list, which means that this algorithm can be used for a linked list. This is one of the few sorting algorithms for a linked list. Right, there's not that many that can be used. This is one of them. The other one is even quicksort can't be used unless you've got doubly linked lists. Right? But for a singly linked list, you can do it here, which is pretty awesome. Because you only really need to know the start position of each system, right? You don't have to know you don't have to be able to backtrace. Even for quicksort, you technically don't need it, but it does make it a lot easier. Okay, can I move you? Thank you. So then in this case, what's going to happen when we merge them back together, for example, when we merge this 4 and this 3 here, we're just going to put them in order, right? And so when we merge this 2, we're just going to put the 2 at the front. And then when we merge this 0 and this 1, we can get this. And then when we merge these, we're going to end up with this, right? And we're done. There's a variation of this called block sort, and what it basically does is instead of stopping at one element, like here, it stops at k elements, which is a constant. Right? So what this means is if k, let's say, equals like 16, it's going to stop at 16 elements. So once there's 16 or less elements in the array, and then it will sort that manually. And the sort it can use manually is maybe even just like a literal hard-coded sort. So an example would be literally just like basically a bunch of if statements saying, hey, if this value is less than this value, and so on, right? If A is less than B, I don't know, and B is less than C, then swap them or something like that, right? Or you could just show a bubble sort because the list is so small, it doesn't really matter. And so you can make all these presumptions about the set. And then selection and insertion sort are basically the same thing. I'm not really going to go through them except for when we actually write the code for it. Yeah, okay, that's good. And the basic idea of both of them is that all you're going to do for the selection sort is go all the way through and find the smallest element and move it to the front, as you can see here. And it's just going to swap it with the first element. So it finds the smallest element, swaps it with the first one, finds the second smallest, swaps it with the second one, and so on. Alright, so in the case of, 4321, it goes find the smallest element 1, swap it with the first one. Find the second smallest element 2, swap it with the second one. And then find the smallest element, swap with the third smallest, and swap with the third one. Find the next one, and swap with the fourth one, and so on, right? So effectively you end up with this constant swapping. And it's going to keep going all the way through until it reaches the point, right? And typically it will swap I with itself. In some cases like this, where we'll go, okay, here, just swap it with itself, so it won't do anything. Okay, and then basically in selection sort is similar. So that is selection sort. Insertion sort is similar, and we can go through that once we do the end. They actually want us to do immutable selection sort. But yeah, yeah. The idea is the same. And there's a bunch of ones online. You can look at all the algorithms if you want, but the concept between selection and insertion sort is actually quite similar, right? So they're doing the same kind of idea. It's just kind of whether or not you are grabbing the biggest one or whatever, right? Let's just continue. Okay, so stable versus non-stable. So we're going to sort this stuff using stable versus non-stable based on name. So the rough idea here, if I go and copy this table, is that stable sort keeps the relative ordering between pairs and non-stable doesn't. Here we go. So, oops. So for example, we note here how there's 2 Johns. A stable sort would state that when we're sorting these, this one will always be before this one because we want to keep the relative ordering. So if we stable sorted this, we'd first sort atoms. Again, this one would be before this one because it occurs before. So when we're sorting, we're going to still get the same kind of ordering. So we would get, atom 1, 2, 3, 1. Math. I can't do that. Math. And then we'd get atom psych 1011. And then we get the next one, which is Jane. So just Jane with the same thing. And then after that we get John, which is COMP2521, and then John, what was that one? Math 1, 2, 3, 1. So you note how this ordering exists. So 1921, 1927 is before 1231, and we reserve that ordering here, or we preserve it, right? And so that's why it's called stable, right? So for example, the typical conditions that's given is that for an item A, that is equal to a what we call tuple or pair of AB. Instead of calling A, I'm going to call X, right? If X dot A is less than Y dot A, right? And sorting on B, then the result the position rather, I guess I should say. So I'm going to say like the position of X has to be before the position of Y, right? After we sort. So if this condition holds, in this case, this does hold, right? This is before this, right? Then once we sort it, we're going to keep that condition, right? And then this doesn't necessarily have to be less than, but rather this is just like the position, I guess we could say. So we could say like the old position of X is less than the old position of Y, right? That's probably better than using a tuple, right? Okay. And then there's this code here, it's like the stable, we'll talk about that later. I don't want to talk about it right now. Yeah, okay, good. So then let's look at week 8, which is actually going to be the fun week. How's time going? Time's good. Okay, so we have functional stuff, right? So let's first talk about functional pointers. So you know what a pointer is, right? A pointer is just a pointer to some data, typically. For example, for example, if we have like this means, hey, this points to an end, right? But sometimes we want more than that, right? So for example, sometimes we may run an array of pointers, right? So we run like 30 arrays, 30 pointers, and so on. And so sometimes this can get a bit hard to read. And so there's a bit of a guide here of how to read this. Effectively, what happens is you always start at the identifier, which is what this thing is called, the name of your variable, and you read the following symbols right to left, kind of. Right? It's a bit confusing, but basically you always prefer reading the array over reading this. It's like an order. So the first order is you always read arrays first, and then you read asterisks, and then at the very top you read parentheses, right? So for example here we read this as P is an array of pointers to integers, right? Because we go out. Now if we had a slightly different example where we have parentheses here, we read this as P is a pointer to, then we go back to the array of events. Right? So you have a pointer to an array of ints. Okay, I don't have the example here, but that's basically what happens, right? And so a functional pointer is a bit different. A function pointer basically states that, hey, let's say we have a function like this. What this does is it takes in a number and it squares it, right? But maybe we've got another function here that does an increment. Right? We have a bunch of these functions and we want to call them on the same set of data. So we want to just have something that says like, maybe like transform, right? So a function called transform, it's going to take in our function and take maybe in an array and a length. And it's going to go through that array, for into I equals 0, I is less than length, I plus plus, right? And at each point, it's going to go like array of I is equal to our function of array of I. This is sometimes called a map, right? i.e. we're mapping our data from a domain to another domain, right? So we're transforming it, right? And we can see here, this is what this is called, map. And this does the same thing, but for a linked list, right? It goes, hey, while the list is not empty, change the head by using this function, and then map the rest of the list. So when we're talking about functional, there's two operations we can use. The first operation is head, and the second one is tail. Head always gives us the first element, and tail gives us the rest. This is often mistaken. A lot of people, especially some people in this course and other people, will make this mistake. I've definitely made it before, where what they'll say is they'll go, okay, tail is the last element. And tail is the last element, typically. For example, when we're talking about linked list, we always talk about tail being the last element. But when we're talking about functional programming, it always defines tail as the rest of the list, not as the last element in the list. So typically what it's defined is this, x, xs, right? So this is the first element, and this is an array of other elements called the rest. And so often this is called the head, and this is called the tail, right? So you have x appended or followed by a series of x's, which is why it's called like this. Okay, so how do we define this function? Well, what we want to do is we want to define a function type. So what we do is we first define the type. All our functions always have to return an int because they're transforming an int. And then we define what they take in. But before we do that, we have to first define the name. So what we do is we define int, and then we give it parentheses, and we give it this special asterisk, and we give it a name. So in this case, we're going to call it fn. You can call this whatever you want. You could call it like, map function. Like this is your name. And then we're going to give it a list of arguments. In this case, it just has a single argument, int, which we can call x. You don't even need to give this a name, it's fine for our name, right? And we can see here, this is what we've just done here. Now what's weird about this is that we can type def it, and if we type def it, we don't have to apply an extra thing after it. So normally with type def, you have to apply an extra thing after it. With functions, you don't, because the name is here. So where the name is different. It's kind of like an array, where the array has it after. So for an array, you have the name in the middle, right? Where normally the name is at the end, right? It's in between these two elements. With a function, it is also in the middle. But instead of having the array brackets, we have another set of parentheses here, right? So instead of having the array brackets here, we have another set. Okay, and then every time we want to call it, all we have to do is do a dereference and then just call it like that. And this will give us back whatever result we want. So it's a function that we can pass around. That's all it is. It's pretty awesome. And so if we want to trace, I'm not going to trace this one, I'm going to trace the next one. fold, just for time purposes. I think we've already gone through this one pretty easily. And then we'll come back to Haskell in a second. So if we look at fold, right? So a fold is basically going, hey, we want to fold over a set. So for example, if you have 1 plus 1 plus 2 plus 3 and so on, right? This is a fold, right? Now the order of the fold is important. So we got either that order or we got this. Wait, that's the same thing. Oops, other way around. Got either that order or you got this order. There we go. Right? So there's two orders here. There's fold left and fold right. So this is a right fold. Right? So as you can see here, there's two folds and they've given an example here. So it computes f of L1, comma, f of L2, comma, f of L3, and so on. Right? Which looks something like this. Right? It folds to the right. Awesome. Okay. And it keeps going all the way to the middle value. So what this means is it's going to calculate this value first, then go backwards. Where here it's going to calculate this value first and go this way, right? Now, there's also a left fold. It looks like this. Now, what's interesting about left fold is it evaluates left to right, where right fold evaluates right to left, right? So that's a useful case for it. There's a bunch of other useful cases there. You can think about what's the most useful, but it does the rightmost first. But the most important about the left fold is that it doesn't have to necessarily do recursion. It can do tail call recursion, which is really nice. Whereas with a right fold, it has to do a stack, right? So it has to like store all the previous results. So if we copy and paste this function in, and this, new page, bang, right? And then we look at this and we trace what the result is. So we have 2, 3, 4. This is a pretty small example, so we'll get it through it pretty quick. Right? This is our list. Right? Then maybe we got like a no element or something like this. So it doesn't really matter, right? Because we always check if it's empty. Then all we're going to do is we're basically going to go, okay, we're going to want to do it so that we multiply all our values together. This is the point of a fold. A fold, it's also something that's called a reduce, right? It reduces the values from many down to just one. So it sums all the values up, it multiplies all the values together, it does a lot of things. In this case, it's going to multiply it all together. So the first thing we need to give is we need to get z. Z is basically the initial value. It's what it's going to multiply the very last value by, or in this case, add the very last value by, as in the previous example. Right? So when it goes here, this plus 3 really adds like a plus 0 here or something. Right? Same thing here. Right? A little hidden, basically a hidden case, right? A hidden last version. So in this case, it's going to go, okay, we want to do f of the head of the list, so 2, right? Multiplied by, so you see, our multiplication function takes 2 arguments. So it's going to multiply 2 by the fold of 3, 4, with 1 being our fold value, because that 1 gets passed through, right? So it looks like this, right? And then it's going to go, okay, and this is going to evaluate to f of 3 times the fold of 4, 1, which is going to be f of 4, 1, which is going to equal 4 times 1, which equals 4. And then this is going to equal f of 3 times 4, right? Because we grab the 4 from before, right? It's 12. And then this is equal to 2 times, or I should say f of 2, 12, right? Which is equal to 2 times 12, which is equal to 24. Right? So these times together and then times by this, or it looks like this, right? And we go right to left. Awesome. Okay, so let's talk about like kind of how this looks in like a more of a functional language, and then we're going to go Fibonacci, and then we'll talk about this in a second. So if we're talking about Haskell, Haskell is quite awesome. So Haskell basically allows us to do all this functional stuff.